Good day, Bayaw. Today, we have here another problem from the book of Thermodynamics by Singal, Chapter 6, The Gas Cycle. A four-cylinder, four-stroke, 2.2 liters gasoline engine operates on a Otto cycle with a compression ratio of 10. The air is at 100 kilopascal and 60 degrees Celsius at the beginning of the compression process, and the maximum pressure in the cycle is 8 megapascal. The compression and expansion processes may be modeled as polytropic with a polytropic constant of 1.3. Using constant specific heats at 850 Kelvin, determine the temperature at the end of the expansion process, the net work output and the thermal efficiency, and the mean effective pressure. We will be identifying our given first. So we have here the gas constant of our air that is equal to 0.287 kilojoules per kilogram Kelvin, the volume of our piston that is 2.2 liters, the compression ratio that is 10, the pressure at state 1 that is equal to 100 kilopascal, temperature at state 1 is equal to 60 degrees Celsius, the pressure at state 3 that is the maximum pressure 800 megapascal, the polytropic constant that is 1.3, the TSat or the saturation temperature that is 850 Kelvin. So we will be finding the temperature at state 4, the work output, the thermal efficiency, and the mean effective pressure. So here, to find our constant pressure of specific heat, we will be using the linear interpolation. Here is the equation. The temperature top minus the temperature bottom over the temperature of our saturation minus the temperature bottom is equal to the constant pressure of specific heat of the top minus the constant pressure of specific heat of the bottom over the Cp that we will be finding minus the constant pressure of specific heat in the bottom. The constant pressure of specific heat at 850 Kelvin is equal to the Tsat minus the Tbot or the T-bottom times the Cp of the top minus the Cp of the bottom over the T-top minus the T-bottom plus the Cp of the bottom. Here we'll be plugging in our values. We have the 850 minus 800 Kelvin times 1.121 minus 1.099 kilojoules per kilogram Kelvin over 900 minus 800 Kelvin plus 1.099 kilojoules per kilogram Kelvin. And we have here the constant pressure of specific heat of our TSat that is equal to 1.110 kilojoules per kilogram Kelvin. Next, we will be finding also the constant volume of specific heat of our TSat with the same linear interpolation. So, we'll be plugging in the values. We have the 850 minus 800 Kelvin times 0.834 minus 812 kilojoules per kilogram Kelvin divided by 900 minus 800 Kelvin plus 0.812 kilojoules per kilogram Kelvin. And we have here the constant volumes of specific heat of our TSat that is equal to 0.823 kilojoules per kilogram Kelvin. Next, we will be finding the temperature and pressure at state 2. So this process in state 1 to 2 is called the polytropic expansion. So we have here the equation that is T1 over T2 is equal to V2 over T1 raised to n minus 1. And since our compression ratio is equal to V1 over V2, we reciprocate this equation here. So we come up with this final equation that is the T2 is equal to T1 times the V1 over V2 raised to n minus 1. We substitute our values. We have this, the T2 is equal to 60 degrees Celsius plus 273 Kelvin times the compression ratio, that is 10 raised to 1.3 minus 1. And we come up with this temperature at state 2 that is equal to 664.4 Kelvin. Next is this equation. We have here the P1 over P2 is equal to V2 over V1 raised to n minus 1. So again, we reciprocate this equation. So we come up with this P2 is equal to P1 times V1 over V2 raised to n. Now, we'll be substituting all the values we have. So we have here the 100 kilopascal times 10 raised to 1.3, and we have this pressure at state 2 that is equal to 1995 kilopascal. Here in process 2 to 3, that is called the constant volume heat addition. So we have here the equation of our combined gas law, the P2 times the V over T2 is equal to P3 times V over T3. And we rearrange this equation to have this the equation of our temperature at state 3 that is equal to T2 times P3 over P2. We plug in now our values. We have here the 664.4 Kelvin times 8,000 kilopascal over 1995 kilopascal, and we have this temperature at state 3 that is equal to 2664 Kelvin. And now we have this equation here of our specific heat input that is equal to the specific internal energy at state 3 minus the internal energy at state 2. That is also equal to constant volume times the temperature at state 3 minus the temperature at state 2. And now, since we have our final equation, we'll be plugging in our values. We have here the 0.823 kilojoules per kilogram Kelvin times 2664 minus 664.4 Kelvin. And we have the specific heat input that is equal to 1646 kilojoules per kilogram. After in process 2 to 3, we will be going into the process 3 to 4, which is called the polytropic expansion. And here's the equation to get the temperature at state 4. We have this, the T3 over T4 is equal to V4 over V3 raised to n minus 1. And since we know that R, or the compression ratio, is equal to V4 over V3. So we reciprocate this equation, and we have this equation here of our T4, or the temperature at state 4, that's equal to T3 times V3 over V4 raised to n minus 1. And now we'll be plugging in our values. We have here the 2664 Kelvin times 1 over 10, since our compression ratio is being reciprocated. So that is now in 1 over 10 raised to 1.3 minus 1. And we come up with this temperature at state 4 that is equal to 1335 Kelvin. So to find the pressure at state 4, so it is state 4. State 4. We'll be using this equation here. We have this, the P3 over P4 is equal to V4 over V3 raised to n minus 1. And again, we reciprocate these equations, and we come up with this P4 is equal to P3 times V3 over V4 raised to n. So we'll be plugging in our values. We have this 100 kilopascal times 10 raised to 1.3, and we have this pressure at state 4 that is equal to 1995 kilopascal. Here in last process 4 to 1, which is called the constant volume heat rejection, we have here the specific heat output that is equal to internal energy at state 4 minus internal energy at state 1, that is also equivalent to specific volume of specific heat times the temperature at state 4 minus the temperature at state 1. And we will be plugging in the values to get the specific heat output, we have here the 0.823 kilojoules per kilogram Kelvin times 1335 minus 333 Kelvin, and we come up with this value of our specific heat output, that is 824.8 kilojoules per kilogram. And now, to get the value of our network output, we have this equation here, the specific heat input minus the specific heat output. And since we have these two, we will be plugging in our values. We have here the 1646 minus 824.8 kilojoules per kilogram, and we have here our network output, that is equal to 820.9 kilojoules per kilogram. Next is our thermal efficiency. We have here the equation of our thermal efficiency, that is the work net output over the specific heat input. And since we have these two now, we'll be plugging in the values. We have these two 820.9 kilojoules per kilogram over 1646 kilojoules per kilogram. And we have this, the thermal efficiency of our Otto cycle, that is 0.499. Lastly, to get the mean effective pressure, we have this equation here. The MEP, or MEP, is equal to network output over the specific volume at state 1 minus the specific volume at state 2, that is also equal to network output over the specific volume at state 1 times 1 minus 1 over the compression ratio. So to have the value of our specific volume, we'll be using this equation here, the ideal gas equation, that is PVRT. So we rearrange the equation and we come up into this specific volume at state 1 is equal to the gas constant of the air times the temperature at state 1 over the pressure at state 1. So plugging in the values, we have the 0.287 kilojoules per kilogram Kelvin times 60 degrees Celsius plus 273 Kelvin over 100 kilopascal. And we come up with this specific volume, that is 0.9557 cubic meter per kilogram, or it is also the specific volume at maximum. And now we have the value of our specific volume. We plug in our values. So we have here the 820.9 kilojoules per kilogram over 0.9557 cubic meter per kilogram times 1 minus 1 over 10. We expand the value of our kilojoules, that is in kilopascal cubic meter. So to cancel the units. And we have here the mean effective pressure, that is equal to 954.3 kilopascal.